of the system. So it is very simple. So how it goes? We draw a
So
square.
your screen is not visible.
Screen isn't visible. Okay, sorry for that. So how about now? Yeah, it should be visible.
Yes, sir. It's fine.
Okay, so what is the block diagram? So the simplest way is draw a box, and in that box we write a transfer function. Draw an outward arrow mark. It represents the Laplace transform of output signal, and an inward arrow mark will represent Laplace of an input signal. So we have already known for this for this mechanical system, x of s is the Laplace of output signal or just an output variable, and f of s is the input variable. So the block diagram will have a transfer function, will have an input signal in Laplace transform and output signal in Laplace transform. So how it goes? So we write ms square plus bs plus k inside the box, and we represent x of s as the output, and we write f of s as the input for this particular system. So this is the block diagram of MBK system. Okay. So the more generalized representation can be given by TF is replaced with G of S and output parameters as it is. So in control system terminology, we use G of S more oftenly to represent the plant. Okay. So now MBK system is termed as plant. Okay. So there is a slight difference in pronouncing like system and plant. So they are not the same. So as of now, we have termed the mass spring damper as a system. Okay. So when we enter into unit 3 or 4, I will clearly differentiate the plant and system terminologies. So as of now, you assume both are same. So G of S represents this particular system or the transfer function. So what I can write? X of s equal to we already know from this equation x of s equal to transfer function this particular term into f of s. Okay, this comes on the other side. The denominator is multiplied here as numerator. So x of s is equal to g of s into f of s. So this is how the signals and the transfer functions are represented. So I am particularly highlighting every time as Laplace transform because this particular expression is true only when it is in Laplace domain. Okay, so we cannot write x of t equal to g of t into f of t. Okay, this you will be studying in signals and system. So please remember not to forget about the Laplace term. So this is one way of writing the block diagram. And to be precise or to be specifically, this diagram is called as open loop block diagram or open loop system. This we have already seen in during the introductory classes about open and closed loop. So since there is no signal coming as a feedback here, we call it as an open loop block diagram or just a, in simple words, open loop system. So next we proceed with another kind of a block diagram, which is called as closed loop transfer function or closed loop system or closed loop block diagram. And in a short form, it is pronounced as CLTF. So whatever we did here is OLTF, open loop transfer function or open loop block diagram. So this is CLTF, closed loop transfer function. So before starting with a closed loop transfer function, let me give a detailed introduction about what is actually a closed loop system, how we can compare that to a practical scenario. So let us consider one practical example of human brain and eyes. Human brain and eyes as a system elements. So first I will draw a summing point. So from the input signal, first we draw a summing point. We'll understand the reason for it soon. Then a square box to represent the plant. then an output signal. So from the output signal, I will draw another block, and the output of that feedback block, to be precise, this is a feedback block, I will join it with a summing point. So now this input, I will term it as a reference input. Reference input. Some textbooks mention it as a command input. Then this feedback block is called transfer function of sensor or sensor dynamics. Sensor dynamics. So we'll soon understand what is meant by sensor dynamics. And I will call it as H of S. Okay, H of S. And this is plant. We represent it as G of S. So we need to understand some points here. Okay, plant dynamics. And this is output. So now I will start with the first element, which is called as summing point. Summing point. And this particular point from where we have taken the feedback is called as takeoff point. Okay, takeoff point. So a summing point will have signals coming and joining towards it. And accordingly, the sign of the signal is marked. So here I am marking plus for the reference input and minus for the feedback. Okay, negative for the feedback signal, I can say. So this signal coming out from here is passed through this sensor block and the direction is as shown. Okay, and then we can call this signal getting subtracted from the reference input as feedback signal. Fine. So there are two types of feedbacks. One is positive feedback, another one is negative feedback. So when the feedback signal is subtracted at this particular summing point, it is termed as negative feedback. So it's very simple. Depending on the sign convention, we tell whether it is negative feedback signal or positive feedback signal. So both have a different consequences on the operation of plant. Okay. So one simple example we take up first with a negative feedback is, then you can think about the positive feedback scenario. Okay. So to start with, let us consider a negative feedback signal and let us call this particular complete system as closed loop system. Closed loop system. And to be precise, you can call it as closed loop system with negative feedback. That makes it more clear. Closed loop system with negative feedback. So let us assume one example where it is required to ride your bicycle or bike by a distance of 100 meters. Okay. So I'm giving a reference input to your brain. Suppose if I imagine your brain as some say plant, I'm giving a command signal. Okay, or a reference input that your brain should operate to work or to ride a distance of 100 meters. So how it goes? So that reference input initially is passed to the brain. Fine. So when at the initial position, which I mean to say there is a 0 meters of displacement, there won't be any feedback, or there will be a feedback that 0 meters has been traveled. Fine. So I look at the output, my sensors will look at the output and they will give me a signal, information, feedback information saying that there isn't any displacement at all. So what are my sensors? Eyes will be my sensors. So what is meant by sensor dynamics? So when we go into a practical application of say robotics or something in power system or power electronics, we often encounter a considerable delay in sending the feedback signals. Okay. So what is meant by that? If your sensor is adding up some delay in sending the feedback information, it means it is adding some dynamics in the system. Like whatever you read, whatever the value you read from the sensor at the current state, may not be actually of the current state. Okay, so the delay might have interrupted the reading of the values. So those sensor dynamics has to be considered. If you ignore that, you may end up in undesired output, we can say. So the sensor dynamics is often represented by H of S, and it will obviously come in the feedback path because you are taking the feedback information from the sensor. Fine. So this is how the feedback is sent. Next, the signal E of S. So the reference data is given, the feedback is taken, and the mathematics goes on at this point, and a signal E of T or E of S is represented here, and it is termed as error signal, or sometimes it is called as actuating signal. Okay, actuating signal in the Laplace transform. So why error signal? Let us look at first representation, error signal. So when I say at the initial position there isn't any displacement at all, so you can assume this output as a x of s. Okay, the displacement x of s. When there isn't any displacement, the feedback sends information saying that there is a 0 meter displacement. So 100 meter minus 0 meter, what is the difference? It is 100 meter obviously. So it indirectly indicates there exists an error of 100 meters to reach your goal. Okay, to reach your goal. So that can be termed as an error. Okay, and in other terms, it is called as actuating signal because when we go into practical scenario, okay, this error is sometimes fed to a controller, and the controller will calculate what amount of actual input to the plant is required to reach the desired goal. Okay, I repeat again, in some practical scenario, we will have a controller block previous to the plant. Okay, you can imagine this as bicycle and a brain here, which I have drawn together. You can draw a bicycle here and a brain here. So the error signal is fed to the controller, and controller in turn will calculate what amount of input is required to overcome this error. So that what amount of input to the plant is required is calculated by controller, and that is termed as an actuating signal. So the controller tries to actuate the system. I hope everyone knows the meaning of actuation. It's a general word, you can browse in Google. So the controller will define what actuation signal is required. So I have drawn it without controller, so I can define it as actuating signal also. Okay, so just to avoid more complexity, I have not included any other block here. So in simple scenario, we take this block itself as a plant. A bicycle together with a human body or a controller or a brain together represents the plant dynamics. So therefore it is called as actuating signal. Fine. So this is how the signals flows, and this is how the process goes on. So when actuating signal or error signal is very huge, what we will do, we'll try to ride the bicycle to reduce the error. Okay. So of course this reference input will be, for the present example, it is only one dimensional. I mean, you are moving only in the x direction. That's what you have to assume. Fine. So one dimensional. Therefore, it starts actuating the bicycle. I mean, you start pedaling it towards, say, some direction, some particular direction, and eventually, what happens? You will cover up some distance. So initially it was 0. Then after some time it is 10 meters. After some times it is 20 meters. Fine. So you're covering up the distance. So 20 meters. When you reach the 20-meter distance, it will send the information. Your eyes will send some information saying that you have covered up 20-meter distance. So 100 minus 20, so 80 meters. So actuating signal required to cover up the remaining 80 meters is generated. So it goes on like this, and you will eventually reach, say, final point. And at 90 meters, suppose you travel 90 meters, then your senses will send you have traveled 90 meters. So the error is 10 meter, error is less. So the actuating signal, say the magnitude or the power, you can say, the power of the actuating signal as you reach nearer to the reference point, will goes on reducing. And finally, when you reach the target, okay, when you reach the target, your error will become 0. Your error will become 0 and you will stop at that particular point. saying the target is reached. Fine. So this is how a closed loop system works. Any queries on this example? Fine. All the terminologies are clear. Summing point and takeoff point, both are different. Then sensor dynamics or transfer function of the sensor, plant dynamics. Then this is called as a system. Altogether it is termed as a system. So now I hope you can understand what is plant and a system, the difference between plant and system. Okay, so to be specific, it is a closed loop negative system, negative feedback system. So I will move on with the next part if there is no doubt. This is how the closed loop negative feedback system operates. So the next thing is how a positive feedback system works. Okay, how a positive feedback system works. So it's a very simple. Mathematically, you can tell it very simple. It is just the feedback is getting added. Okay, the feedback is getting added at every instant of time, and the actuating signal is generated. Fine. But if you think of with some example, you find a very rare number. I mean, in fact, I haven't found very rare number of examples with a positive feedback. Fine, positive feedbacks. But if you just apply the same scenario, I mean, the same example of bicycle riding with positive feedback, do you think you will end up with a right target? Can anyone answer me? Consider the same example of riding the bicycle and reaching a target of 100 meters, where we have now say positive feedback. Instead of getting subtracted, your feedback is getting added. So do you think that will be the proper operation of the system, brain?
No, sir.
No, not possible, right? Okay, to give another way of interpreting this, now instead of human brain, you add one robot, actual robot, where you can code the brain in a manner whichever you like, and you make the feedback as positive. Imagine that robot's eye is giving a positive feedback. So if that is the scenario, your robot will never end up at the exact destination, right? Everyone is able to understand?
Yes, sir.
Okay, Abdul Bakar, are you following?
Yes, sir.
So it is not possible, right?
Yes, sir. Not possible.
It's not a right way of operating the system. Fine. So negative feedback will always improve, the behavior of the system. Correct? Do you agree with this? Whom should I call now? Aditya Bhaskaran? Aditya
Yes, sir.
Bhaskaran. Can we conclude
sir.
negative feedback will improve the system behavior?
Yes, sir.
Okay, then Ishit.
Yes, sir.
Correct?
Yes, sir. It will
Okay,
improve.
it will improve. So this is a brief difference between negative and positive feedback and about a closed loop system. Fine. Okay, that's a part. Then we'll move on to the next part.
Sir, if you want to, for example, if you want to just know how
Mhm.
long have you walked, so you may need just positive feedback.
How long it will work? Huh?
Now, how long if you have walked or run,
Hmm.
you just want to know the distance. You don't want to know whether you have reached a destination. You just want to know
Mhm.
the kilometers that you have traveled. In that case,
Hmm.
positive feedback will improve the system.
Yeah, see, I'll tell the consequence of positive feedback. Maybe that will answer your question. Suppose imagine we have taken the same example. Okay, I'll put it again for the sake of understanding. So for this particular example, again, imagine there is a positive sign here. So initially 100 meter and you start riding anyhow because there is no signal. Initially it sends a feedback signal as 0 meters, right? So you start riding the bicycle. And after covering 100 meter, okay, after covering 100 meter, sorry, 10 meter. After covering 10 meter, what will be the error signal magnitude? It is 100 plus 10, 110. Okay.
Sir, excuse me, sir. You can start with 0, right, sir? Instead of 100, and then add on the 10 meters and get to 100.
You can start from 0. My reference input is 100 now.
Okay, sir.
See, target command signal is like always some non-zero value, right?
Yes, sir.
So command value should be non-zero. So I'm taking the command signal or the target signal to reach 100 meter. There are some other scenarios in the advanced control theory where we want to bring from, say, some non-zero value to zero value. They are quite different. But for this particular example, I cannot initiate from 0 meters as a command signal. Have you got this?
Yes, sir.
That is one way of operating the system. What you told is fine. You start from 0, then compare with some value and all. Eventually, it will come down to the same concept. It's not different.
Okay, sir.
So we take 100 meter, and once we reach 10 meters, the information passed is to actuate the system saying that you are at 110 meter distance. Fine. So it's not a right information you are passing. That is one thing. Correct?
Yes, sir.
And another thing, when we pass the wrong information, the bicycle or the robot will try to bring back or drive in opposite direction, ride the bicycle in the opposite direction. So together the system is like behaving abnormally. You are not passing the right information, that is first thing, and the wrong information is accepted by the robot and it is trying to ride back in the reverse direction. So altogether it is like it is going to some undesired behavior. Fine.
Yes, sir.
So like if you compare with oscillator scenario, this actual example is quite different. So it is as good as you are passing the wrong information and the system is not operating properly. So positive feedback is not preferable. This is the conclusion. Fine.
Yes, sir.
Anybody else has any queries? So the ultimate conclusion is never try to prove that the system behaves normally with the positive feedback. Okay, it doesn't work in all the scenarios. Only some examples like oscillator, you can prove it mathematically. Fine, that's the thing. And moving with the next example where I had stopped. So we studied open loop and the scenario of closed loop with positive and negative feedback. Next, we will move on to something called closed loop transfer function. So let me consider a closed loop system with a negative feedback. As shown. Let me see how many are left. Sachin Chavan, are you following? Shashank RC.
Yes.
Shweta Rajgopalan.
Yes, sir, following.
Sri MS. Shrikar. Are you following?
Yes, sir.
Okay, fine.
Sir, I ask my name.
Shrikar.
Yes, sir.
Okay. So this is the system we'll consider, and we will now derive the transfer function for this particular block diagram, which is called as closed loop transfer function. This is open loop transfer function, and obviously there is a difference between these two. So let us see how the closed loop transfer function can be derived. So as I said earlier, feedback can be positive or negative depending on our particular
So
application.
can it be a combination of both positive and negative?
No, it can never be.
So
Okay.
like if you want to, let's say,
Mhm.
raise the level of water
Mhm.
and you send a feedback back to the, let's say, geyser. It's too little water, so it increases the water. What if it reaches a point where it's more than what the rated value of the tank is? So that way you should have a negative feedback, right? So you can drain out the water.
That is also taken care in the negative feedback. I will explain it briefly. Suppose
Okay.
forget about this block diagram. and imagine you are filling the water tank. Water tank example is fine. So
Yes.
imagine you are filling it and your target is filling it say for a height of 10 meters. So you start filling it and you have say put one sensor which measures the current height of the water level. So at start the height of the water is how much? 0 meters. Fine. So the error signal is 10 minus 0. Fine.
Yes, sir. Correct.
So the actuating signal operates the motor saying there is a 10 meters of difference. So start the valve, some kind of actuating signal.
Okay,
Then
sir.
eventually it fills up and suppose imagine it goes to 11 meter height.
Hmm.
So error
So
is
I'll get
10 minus
-1 error
11
signal.
minus 1.
Hmm.
So minus 1 actuating signal in the sense you can interpret it like you are generating an actuating signal uh, to make or to operate the motor in a reverse direction.
Okay, okay.
I mean, it should take out some water.
Okay, fine.
So the same kind of feedback will take care of both.
So then technically even the additive feedback thing should do the same, right?
No. how it is possible? See, if you are giving a feedback and by the moment motor has filled a 1 meter height of water, you are passing an information to the motor saying that you are having excess of water, 10 plus 1.
Okay, okay.
So,
So then why would you ever have a positive feedback system?
that
What
type
is the use of one?
no. See, some things no. When we say make a theoretical study or derive one theory, we have to understand conceptually the effect of positive and negative wherever. Okay.
Hmm.
But in some scenarios, there doesn't exist any effect of positive at all. In the sense, it will never get used actually.
Okay, okay. So it's kind of useless.
A kind of useless only. There's no doubt.
Okay, okay.
Okay, only in the oscillator I could find it. But
I
the
don't
way
understand how it's useful in oscillator. So how would it be useful in oscillator?
oscillator, we will take it in another class actually. That's a different story. So
Okay.
we will restrict to the practical dynamical systems. So
Okay,
I
fine.
feel it was never used.
Okay, okay.
Okay, though technically, mathematically, we can say positive is a parameter, but it is not useful at all.
Okay, sir, fine.
Fine. Okay.
Fine.
So we draw an actuating signal. And let us see how things can be represented in this diagram. So first we start with the C of S. It is the Laplace of output signal, which I have already told. And there is another terminology used for C of S. It is called as controlled output. So as I said earlier, before the plant there comes a controller, and controller will operate or actuate this plant. So we often refer this output as sometimes, when we operate with actual controllers, we call it as controlled output. But you can just call it as output of the system. And R of S, as I said, it is reference input. Then E of S is error signal or actuating signal. So all are in Laplace. So can you imagine, like our brain is having so many feedback sensors. Okay. So to proceed, if H of S is 1, unity. Okay, if H of S is unity, it is called as unity feedback system. Unity feedback system. Unity feedback system, and how we can interpret the unity feedback system means the sensor dynamics is equal to 1. Okay, sensor dynamics is equal to 1 in the sense whatever it reads at the output side is immediately sent to the summing point, back to summing point without any delay. So if H of S is equal to 1, this block is like shorted. Okay, it will not become 0. Okay, please understand H of S equal to 1 means these 2 points will be shorted. and the sensor dynamics is 0. Therefore, whatever value it reads, it will immediately send to the summing point, back to the summing point immediately. So whatever the value is read at this summing point is its current output value. But if it is not 1, not equal to 1, instead if it is equal to say some delay, okay, then it will never be sending the immediate value. There will be a delay. So whatever the summing point actually is reading is actually the value at the output at a previous instant of time. So now for time being, you understand what is HFS equal to 1, which means the dynamics of the sensor is unity with no delay at all. Next, what is C of S by R of S? I request everyone to take this diagram. We'll make a small derivation. So please take this closed loop block diagram. Somebody please remind me one at 5:10. Okay, I will be continuing. Take this block diagram, please. We are going to make a small derivation now. Okay. So first step of the derivation. First step of the derivation is to find what is E of S. Okay, what is E of S? It's very simple. E of S is a subtraction of two signals. I mean, plus from RFS and minus from a signal coming from this point. Okay. So we already know in the previous example that X of S equal to G of S into F of S. We already wrote that at the output of any block, okay, at the output side of any block, we write X of S equal to transfer function multiplied by its previous signal. Its previous signal. So similarly here, one can say E of S equal to R of S minus the transfer function in this path, which is H of S, multiplied with a signal coming to this transfer function block, which is C of S. So E of S equal to R of S minus H of S into C of S. Fine. So E of S is equal to R of S minus C of S into H of S. Any doubt on this equation? Should I repeat again?
No, sir.
Okay. Next, we'll move on to the step 2. So look at a block diagram parallelly. Now we need to write the expression for C of S. So what is C of S equal to? C of S, look at the flow of the signal, direction of flow of the signal. Signal is coming from G of S, which is transfer function, and its previous signal is E of S. In a simplest way, we can tell E of S multiplied with G of S will give you C of S. If you want, you write it down or just look at this video carefully. So these are the two expressions which are sufficient to find our answer. So now you can make a substitution of C of S in the in the equation 1 or step 1, or in other way you can substitute E of S in the step 2. So both will simplify our task. So I'll do the second one, substitute E of S in the equation 2. So we have R of S minus C of S into H of S. Fine. So what we need ultimately, we need the transfer function C of S by R of S, output Laplace divided by input Laplace. So simplify. So C of S is present on both LHS and RHS. So use a simple mathematics. I will take this C of S part on the other side. So it will become positive. So you can write C of S plus C of S into H of S into G of S equals to R of S into G of S. So that way you can make out. So C of S, then I'll take it common on the LHS side. So it will become G of S into H of S plus 1. equals to R of S into G of S over what we need ultimately C of S by R of S. Take this R of S on the other side, the terms in the square bracket on the right hand side. Okay. Okay. So is this what everyone got? So now please look at the diagram and this final expression. If we have a negative feedback system, its closed loop transfer function is G of S divided by 1 plus D of S into H of S. Is it clear for everyone?
Yes, sir.
If anybody else has any doubt, you are open to ask. Fine. So we are done with the closed loop transfer function, and this is what the block diagram representation for open loop system and closed loop system is. Okay. So basics of block diagram system. So still there is 5 minutes of time. I think I should stop here. I'll just give one simple example of okay, one simple example of block diagram reduction technique. So block diagram reduction technique was one of the topic which I have skipped for your syllabus. You won't be getting any numerical on this. So whatever this numerical I am showing right now is just for the sake of understanding. So in a complex system, you may have a system blocks, system elements, which can be represented like this example. Okay. So a closed loop inside the other closed loop. Okay. The task is reduce this block to a single block. Reduce this block diagram to a single block. So how to solve this? So both, this is one closed loop, this is another closed loop, both have a unity feedback. To start with, we'll consider the first simplest block, which we have already solved. Closed loop, which is a closed loop. For this closed loop, our H1 is 1, therefore we will directly get G1 divided by 1 plus G1 as the block, reduced block for the inner closed loop. So it will be reduced like this. So now the inner closed loop is reduced and it is replaced by G1 divided by 1 plus G1. Fine, H of S is 1. Now I will call this particular block as G dash. For the sake of simplicity, I will call it as G dash. And G dash is having again a unity negative feedback. So what will be our block diagram? Sorry, the transfer function. It is G dash divided by 1 plus G dash. Very simple. So when I write G dash divided by 1 plus G dash, this closed loop vanishes and we will have a single transfer function. So let us replace G dash term. So G dash is G1 divided by 1 plus G1. Then the rest is a very simplest steps. So please calculate yourself. So final answer is it G1 divided by?
Yes, sir. G1 by 1 plus 2 G1.
Yes, G1 divided by 1 plus 2 G1. Fine. That's it for today's class, and we'll continue with the other things in the next class. Thank you all.